When deploying cloud workloads, it is easy to assume your containers act as hard security boundaries. They are actually far more porous than they appear. Standard containers favor speed and efficiency, but that thin layer of separation has a structural limit. When put under internal pressure, the isolation fails. This diagram shows container blocks on a shared host kernel. If an attacker breaks out, they gain direct access to everything. AI agents amplify this by autonomously generating untrusted code, constantly testing the limits of that shared kernel. Traditional security policies rely on predictable, static behavior. They cannot account for autonomous agents making their own resource decisions in real time. Running untrusted AI code in a standard container compromises the entire host architecture. A single escape grants access to every other workload sharing that hardware. To secure these multi-tenant workloads, you have to build an architecture based on two distinct pillars. Pillar 1 is architectural isolation, the structural barriers designed to physically prevent a container escape. Pillar 2 is runtime visibility, the monitoring layer required to detect anomalies and ongoing attacks. Navigating this requires a clear trade-off. Hardware-level security often means giving up sub-millisecond boot times and accepting higher operational complexity. Miscalculating these trade-offs leaves you with one of two outcomes: a system that is structurally vulnerable to breach, or an engineering team overwhelmed by infrastructure maintenance. The first tier of isolation is gvisor. Instead of a full virtual machine, a proxy layer called the sentry intercepts system calls in user space before they reach the host. This approach is fast. Avoiding a guest kernel gives millisecond startup times. It runs without KVM virtualization, deploying easily in cloud environments where nested virtualization is restricted. The trade-off is a performance tax. This interception mechanism adds significant latency, slowing I/O-heavy workloads by up to 30%. gvisor works well for CPU-bound, ephemeral tasks. However, it does not provide the hardware-enforced boundaries required for highly adversarial environments. For those environments, you need Tier 2 isolation, micro VMs, managed by orchestration frameworks like Kata containers. Kata uses back-end virtual machine monitors, like the Firecracker VMM, to provision a dedicated, isolated guest kernel for every individual workload. This diagram shows workloads encased in KVM-enforced hardware boundaries. Giving each agent its own kernel physically removes the shared kernel threat. But this security comes with a latency cost. Spinning up adds 300 milliseconds to boot time and requires infrastructure supporting nested virtualization. Some run raw Firecracker to reduce overhead, but custom micro-VM orchestration requires managing kernel images, network jails, and root file systems manually. Despite slower startup, micro-VMs are the required architectural standard for running multi-tenant or untrusted code executions. Once your isolation is set, you have to address visibility. Many teams start with isolated eBPF alert generators, like Falco. These tools provide deep insight into system calls, allowing you to see exactly how a container is behaving at a low level. The problem is the noise. Out of the box, these systems create constant alert fatigue, often requiring weeks of manual rule tuning to become usable. During an incident, isolated tools force analysts to manually piece together disparate alerts from 4 different dashboards just to understand the attack. This diagram shows the alternative: full-stack correlation through platforms like Armo-Kadar. Instead of isolated signals, cloud, container, and application events link automatically into a single timeline. This correlation happens with a total CPU overhead of less than 2.5%. Visibility without correlation is just expensive data storage. Using a correlation platform can reduce investigation time by 90%, provided you consolidate your security stack. This flowchart maps your engineering needs against the available technology. It begins with one question: is the code highly untrusted or multi-tenant? If the answer is no, and you're running trusted I/O-heavy applications, use standard containers paired with Tetragon. For ephemeral, CPU-bound tasks on infrastructure without nested virtualization, implement gvisor for syscall-level isolation. But if deploying multi-tenant AI agents or code you don't control, you must use Kata containers to ensure hardware-enforced boundaries. Regardless of your isolation tier, you have to solve for alert fatigue. If your team is spending hours investigating noise, you need to move from isolated monitors to full-stack correlation. This is where scattered, isolated alerts finally lock together to form a single, verifiable, and unified timeline of the entire attack. Defining your risk profile early prevents structural breaches, keeping your team from drowning in operational complexity. Match your architecture to your specific threat model.